millennia. In the United States, the Association of State Floodplain Managers works to promote education, policies, and activities that mitigate current and future losses, costs, and human suffering caused by flooding and to protect the natural and beneficial functions of floodplains, all without causing adverse impacts. A portfolio of best practice examples for disaster mitigation in the United States is available from the Federal Emergency Management Agency. Control. In many countries around the world, waterways prone to floods are often carefully managed. Defenses such as detention basins, levees, ponds, reservoirs, and weirs are used to prevent waterways from overflowing their banks. When these defenses fail, emergency measures such as sandbags or portable inflatable tubes are often used to try to stem flooding. Coastal flooding has been addressed in portions of Europe and the Americas with coastal defenses, such as sea walls, beach nourishment, and barrier islands. In the riparian zone near rivers and streams, erosion control measures can be taken to try to slow down or reverse the natural forces that cause many waterways to meander over long periods of time. Flood controls, such as dams, can be built and maintained over time to try to reduce the occurrence and severity of floods as well. In the United States, the U.S. Army Corps of Engineers maintains a network of such flood control dams. In areas prone to urban flooding, one solution is the repair and expansion of man-made sewer systems and stormwater infrastructure. Another strategy is to reduce impervious surfaces in streets, parking lots and buildings through natural drainage channels, porous paving, and wetlands. Areas identified as flood-prone can be converted into parks and playgrounds that can tolerate occasional flooding. Ordinances can be adopted to require developers to retain stormwater on site and require buildings to be elevated, protected by flood walls and levees, or designed to withstand temporary inundation. Property owners can also invest in solutions themselves, such as re-landscaping their property to take the flow of water away from their building and installing rain barrels, sump pumps, and check valves. Analysis of flood information. A series of annual maximum flow rates in a stream reach can be analyzed statistically to estimate the 100-year flood and floods of other recurrence intervals there. Similar estimates from many sites in a hydrologically similar region can be related to measurable characteristics of each drainage basin to allow indirect estimation of flood recurrence intervals for stream reaches without sufficient data for direct analysis. Physical process models of channel reaches are generally well understood and will calculate the depth and area of inundation for given channel conditions and a specified flow rate, such as for use in floodplain mapping and flood insurance. Conversely, given the observed inundation area of a recent flood and the channel conditions, a model can calculate the flow rate, applied to various potential channel configurations and flow rates. A reach model can contribute to selecting an optimum design for a modified channel. Various reach models are available as of 2015, either 1D models or 2D models. HECRAS, the Hydraulic Engineering Center model, is among the most popular software, if only because it is available free of charge. Other models such as Tuflow combine 1D and 2D components to derive flood depths across both river channels and the entire floodplain. Physical process models of complete drainage basins are even more complex. Although many processes are well understood at a point or for a small area, others are poorly understood at all scales, and process interactions under normal or extreme climatic conditions may be unknown. Basin models typically combine land surface process components with a series of reach models. For example, a basin model can calculate the runoff hydrograph that might result from a 100-year storm, although the recurrence interval of a storm is rarely equal to that of the associated flood. Basin models are commonly used in flood forecasting and warning, as well as in analysis of the effects of land use change and climate change. Flood forecasting. Anticipating floods before they occur allows for precautions to be taken and people to be warned so that they can be prepared in advance for flooding conditions. For example, farmers can remove animals from low-lying areas and utility services can put in place emergency provisions to reroute services if needed. Emergency services can also make provisions to have enough resources available ahead of time to respond to emergencies as they occur. People can evacuate areas to be flooded. In order to make the most accurate flood forecasts for waterways, it is best to have a long-time series of historical data that relates stream flows to measured past rainfall events. Coupling this historical information with real-time knowledge about volumetric capacity in catchment areas, such as spare capacity in reservoirs, groundwater levels, and the degree of saturation of area aquifers is also needed in order to make the most accurate flood forecasts. Radar estimates of rainfall and general weather forecasting techniques are also important components of good flood forecasting. In areas where good quality data is available, the intensity and height of a flood can be predicted with fairly good accuracy and plenty of lead time. The output of a flood forecast is typically a maximum expected water level and the likely time of its arrival at key locations along a waterway, and it also may allow for the computation of the likely statistical return period of a flood. In many developed countries, urban areas at risk of flooding are protected against a 100-year flood. That is a flood that has a probability of around 63% of occurring in any 100-year period of time. According to the U.S. National Weather Service Northeast River Forecast Center in Taunton, Massachusetts, a rule of thumb for flood forecasting in urban areas is that it takes at least 1 inch of rainfall in around an hour's time in order to start significant ponding of water on impermeable surfaces. Many NWSRFCs routinely issue flash flood guidance and headwater guidance, which indicate the general amount of rainfall that would need to fall in a short period of time in order to cause flash flooding or flooding on larger water basins. In the United States, an integrated approach to real-time hydrologic computer modeling utilizes observed data from the U.S. Geological Survey, various cooperative observing networks, various automated weather sensors, the NOAA National Operational Hydrologic Remote Sensing Center, various hydroelectric companies, etc., combined with quantitative precipitation forecasts of expected rainfall and/or snowmelt to generate daily or as-needed hydrologic forecasts. The NWS also cooperates with Environment Canada on hydrologic forecasts that affect both the US and Canada, like in the area of the St. Lawrence Seaway. The Global Flood Monitoring System, GFMS, a computer tool which maps flood conditions worldwide, is available online. Users anywhere in the world can use GFMS to determine when floods may occur in their area. GFMS uses precipitation data from NASA's Earth-observing satellites and the Global Precipitation Measurement Satellite, GPM. Rainfall data from GPM is combined with a land surface model that incorporates vegetation cover, soil type, and terrain to determine how much water is soaking into the ground, and how much water is flowing into streamflow. Users can view statistics for rainfall, streamflow, water depth, and flooding every 3 hours. At each 12-kilometer grid point on a global map, forecasts for these parameters are 5 days into the future. Users can zoom in to see inundation maps in 1-kilometer resolution. Deadliest floods. Below is a list of the deadliest floods worldwide, showing events with death tolls at or above 100,000 individuals. In myth and religion. Flood myths are widespread in many cultures. Flood events in the form of divine retribution have also been described in religious texts. As a prime example, the Genesis flood narrative plays a prominent role in Judaism, Christianity and Islam. See also. References. Bibliography. External links.